Hi there and welcome. This video is a differentiation review based on Calculus 1 material. Specifically, I'm going to be talking about how to use derivative shortcut formulas to find derivatives and also how to determine increasing, decreasing, and critical points of a function. So I have a few examples here I'm going to go through. I do want to mention that on the Information and Handouts tab on Canvas, I have listed several reference sheets, including something like this. These are some common derivative formulas. So if you don't quite have everything memorized, you can certainly download your own sheet or use one of mine to help you remember the different formulas that you'll need for derivatives, antiderivatives, trigonometry, etc. So please refer to the sheet if necessary. I'm just going to go through because I do have most of these remembered. Okay, so the first one says find the derivative. We have a couple of functions here. We have a square root function and we have a cosine x function, and they're adjacent with no operation between them, which means they're multiplied. So I'm going to have to use what's commonly referred to as the product rule or the multiplication rule for derivatives. That's the derivative of one of them times the other plus the derivative of the other times the first. Let me show you how that works. Before I do that, I'm going to slightly simplify this equation because the formulas, math in general, doesn't work so great with square root symbols or other kinds of roots and radicals. So we're going to write this as a fractional exponent. So let me write my equation using the 1/2 exponent, which is equivalent to square root. And I'll just emphasize the multiplication in there times cosine x. All right, so the derivative, some people write the derivative as y prime. Some people write the derivative as dy dx. And there are other ways of writing the derivative. In Calculus 2, I actually have to tell you that you kind of have to use dy dx, not because I just say so, I guess partially because of that, but reality is there's a lot of formulas that don't work with y prime in this course, especially when we get to integration techniques and more complicated antiderivative things like Taylor's theorem. Those that don't work with y prime anymore. So although you may have learned that as a shortcut sort of abbreviation in a previous course, you're going to have to get used to dy dx. All right, so dy dx is equal to, there are two functions here. There's one function here. There's a second function here. So I'm going to differentiate the first one using the power rule times the second function. And I'm going to add to that the derivative of the second function. The derivative cosine is negative sine. And that is times the first one. So that's how the product rule works. And then I'll just simplify this by combining things together. If I want, I can write this as a positive exponent in the denominator. Honestly, I don't really care. But I'm going to make this look like a slightly simpler fraction. Plus or minus is minus. It's traditional to put the x's in front, so I'll be traditional. And that is the derivative of the function in part A. All right, let's do one that has a quotient rule. So example B, I have a fraction, but what's important about this fraction is that there's a function in the top, namely 2 to the x, and there's a function on the bottom, 3 minus 4 ln x. I know they're functions because they contain moving variables, x's in there. So I have a function on the top, a function on the bottom. That would be different than if I just had a number, like pretend this x was gone. That's no longer a quotient rule problem because it's just got a 2 on top. So, I mean, I guess you could use the quotient rule, but it's overkill and much easier just to use regular chain rule for that problem. Okay, nonetheless, we have this problem here in B. We're looking for dy dx, which is the derivative. And so we're going to start differentiating this. By the way we think of derivatives, if this wasn't clear from your Calculus 1 experience, is a derivative is an operator, which means that we're doing the same thing to both sides. So like I could square root both sides. That would be doing the same thing to both sides, square root being the operator. I could add 7 to both sides. What I'm going to do is I'm going to differentiate. ddx is the verb or the operator to differentiate. I'm going to differentiate the left-hand side. And I'm going to differentiate that looks messy, sorry. I'm going to differentiate the right-hand side, if I can make this look right. So ddx is the verb to differentiate, to take the derivative. And then dy dx is the noun. It is the derivative, right? So that's the difference between those symbols, basically verb versus noun. Okay, so I'm going to go ahead and find the derivative on both sides. The derivative of y is called dy dx. And the derivative of this creature, it's a quotient of 2 functions. So I have this top function up here. I have the bottom function down here. And before I actually do the differentiation, I'm going to write out what I'm going to do just to emphasize this. So I'm going to differentiate the top times the bottom. And then I'm going to subtract, oops, one more parentheses, the derivative of the bottom times the top. And this entire thing is divided by the bottom squared. Okay, so that's just one way of keeping track of more complicated problems is don't try to do everything in your head. Just write out what you're going to do, and the next step, just do it all. So this is a demo of that kind of organizational strategy. The derivative of 2 to the x, it's on your formula sheet. It's 2 to the x ln 2. And then I'm just multiplying by this other creature. And now I have to differentiate 3 minus 4 ln x. A constant being added or subtracted has a derivative of 0. A constant being multiplied or divided to a function, like this 4 is multiplying by the ln x, doesn't go away, but it doesn't affect the derivative. It just multiplies through. So it'd be 4 times whatever the derivative ln x is. And the derivative ln x, if you wish to check, is 1 over x. And so this whole thing, that's the derivative of the thing in parentheses, is being multiplied by 2 to the x. And once again, this entire thing is divided by that very long expression on the bottom. All right, all I'll do is clean this up a little bit, and then I'll have my answer for the derivative of the function in part B. So not much I can do here. I don't really want to distribute. That's very seldom going to help. I guess it does sometimes. But if you can sort of look ahead, these things don't look alike. They do have a 2 to the x in them, but it's not necessary to factor that out. I guess some people write the ln 2 in front, but you get to do your version of what looks nicer. I'm just trying to combine things together. So for example, 0 minus 4 times 1 over x is just minus 4 over x, and times a negative makes a plus. So this would be plus 4 over x times 2 to the x. And once again, we have this lovely expression in the bottom. And there we go. That's our derivative answer for this, fraction of 2 functions, or one function that is realized as a quotient of two other functions. Okay, so those are some examples of the product rule and the quotient rule. Let me do some chain rule practice problems, because chain rule is very common in differentiation. All right, so here I have a problem. It's again, just find the derivative. And I have a sign, and inside the sign is some complicated stuff. And in fact, the sign is in parentheses being raised to the 3rd power. So we have this thing here raised to the 3rd power. So You may remember the power rule. The derivative of x to any number is the number times x to one smaller exponent. And the chain rule basically says you can replace x by anything. Traditionally, they use the letter u. So notice that I'm still differentiating respect to x, but x is not the same as u, right? So I'm differentiating with respect to the variable x, but anything else. I tend not to use u. It looks more complicated to me than it needs to be. I just put like a box. So if I differentiate anything, which I just leave as a box, then the rule basically becomes the same. You get n times this box. Looks like I need a little more space here. Okay. Move it over. So n times the stuff, whatever the u was or whatever you want to call it, to the n minus 1. So you can see the rule is really the same, but instead of x, I have this other thing. And then the chain part of the chain rule is you have to differentiate, again, with respect to x, whatever this box thing was, whatever that u thing was, if you want to use the notation from the math folks. So that's the chain rule right here. This is the chain rule. And you don't have to just do it with the power rule. The chain rule works for any derivative formula, replacing x by anything else, any function that involves the letter x. So you can differentiate it, and then you just have to multiply by this chain at the end, the derivative of that thing that you replaced x by. So it's a kind of a version of substitution where we're substituting something in for x. All right, so hopefully that jogs your memory if you didn't remember a ton about the chain rule. So let me go ahead and do the chain rule for example C. Okay, so well, maybe I'll put this back here. This is my thing raised to the third power. So according to the chain rule, if I differentiate both sides, derivative of this side, derivative of this side, the derivative of y is going to be dy dx. And the derivative of this thing, well, this is thing to the third. So the derivative of thing to the third is 3 times thing to the second, that's the power rule, times the derivative of whatever that thing was. That's the chain rule. So let me fill in the thing. The thing is sine of x squared plus e to the minus x. Sine of x squared e to the All right, so we have done this part. This part right here doesn't have any thing to do. It doesn't have any verb in front of it. It's been differentiated. But this part right here, we need to do because it still says the derivative of a thing. All right, so just to make sure I'm organized, I'm going to rewrite the first part that I did, 3 sine of this stuff. And then I'm going to multiply by the next part. All right, so what is this part? This part says sine of x squared plus e to the minus x. And so this is sine of not x, sine of stuff. Once again, we know the derivative of sine, the derivative of sine x is just cosine x. But this is not sine x, it's sine of some inside function. So the derivative of sine of an inside function is just going to be the chain rule again. So we're going to get cosine, I'll use blue, I guess, cosine of the stuff times the derivative of the stuff. So once again, we applied the chain rule where the stuff, the inside thing now is x squared plus e to the minus x. All right, so continuing on our little journey here, dy dx. Da, 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 da. If someone told you that math wasn't tedious, they are lying to you. I'm gonna write all this stuff just so I don't lose track of it. Now I have to differentiate this last part right here. the derivative x squared plus e to the minus x. These are two functions being added together, so I can take the derivative of each one separately. The derivative of x squared is just 2x. And the derivative of e to the minus x, a lot of people remember that the derivative of e to the x is e to the x, which is correct, but this is not e to the x. It is e to something else. Now, I know it looks very similar to e to the x, right? I know it's like almost x, but the reality is it's not. And anytime you don't have just x, you're going to have to use the chain rule. So the derivative of e to the x is e to the x. So the derivative of e to the stuff is e to the stuff. Go back in black there. E to the stuff times the derivative of the stuff. If I can sneak that in right there. In this case, the stuff is the thing that we've replaced x by, which is just negative x. So even in this situation, we have another chain rule. So this has lots of chain rule practice in this problem. All right. So I think we're almost done here. 3 times the sine stuff times this cosine stuff let's see, I need to use some parentheses here because this thing right here differentiates to this thing right here. I got to be careful that I don't just think I'm adding things on. I'm really just multiplying. Each time you do the chain rule, it's the multiplication of the next derivative. So I need to make sure that I'm doing that correctly. So let me use parentheses just to make sure I don't mess that up. So there's my first thing, my cosine thing, and then I'm multiplying by the next chain, which is 2x. Oh, I have, yeah, 2x plus e to the minus x. And the derivative of minus x is just minus 1, like that. Whew. All right, the only thing I can really do to combine, since these are all just things that are being multiplied together, is take this -1 and multiply by this essentially +1. So I'm going to get the exact same expression at the end, except it's just going to be a minus e to the minus x. So my derivative is just this stuff I have to write over and over again. So I'll just kind of write fast and sloppy. Okay, fast is not making it faster. I got it. I got it. All right, so there's my simplified answer for the derivative of this multiple chain rule problem. Whew. All right, well, I always invite students whenever they feel comfortable to pause the video and give things a try. As much as you can watch someone else do math problems, it really comes down to you doing it to really know if you got it. If trying problems, you get them all right, then you can get a good pat on the back for yourself. If you get stuck somewhere, at least you know where you got stuck. So you need to know how to get unstuck in the future. So then you can watch the video and learn how to get unstuck. It's a great way of helping you learn by being actively doing problems instead of just watching the problems. Okay, so if you have paused and tried part D, great. If you haven't, you can just watch the video. It's fine too. So in part D, I'm asked to find the first and second derivatives of this function right here. So to find the first derivative, I just differentiate both sides. So I'm going to be taking this thing. I guess I'll use blue and differentiate that side. I know it looks a little messy, but you know what I'm going on here. And this whole thing, I'll be differentiating as well. I think that's pretty clear. I know things have been written over a bit, but if you presented this to me, I can easily see that you're differentiating both sides. So it's okay if it doesn't look perfect, pristine. But I'll try to make it look more legible down here since I'm actually doing some math work over here. All right, so to do the derivative of this thing, I have to differentiate 1 over x cubed. As I mentioned before, this is not a quotient rule problem because it's not a function divided by a function. It's a number divided by a function. All right. And we can always use a much easier method than the quotient rule when we don't have a function over a function. The easy thing here is just to write this as a negative exponent. And then we can use the power rule. So the derivative of x to the negative 3 is negative 3x to the negative 4, because remember, we're subtracting 1 off of the exponent. Minus 3 minus 1 is minus 4. The derivative of edx, remember, is a chain rule. We did that one before. So that's a plus sign here. The derivative of e to the negative x is e to the negative x times the derivative of that inside function. And the derivative of e times sine 2x. This is also not a product rule problem because e is not a function. If you're thinking e to the x is definitely a function, but e is a number. If you don't remember, it's about 2.718. Pi is 3.14. Square root of 2 is 1.41. I mean, they're all just numbers unless they have x's with them. So if I have a number multiplied by a function, this is a function because it has x in it, the number being multiplied doesn't affect the derivative, doesn't go away, so it just stays there as e. And I'll have to differentiate the actual function secant 2 pi x. So this is a chain rule problem because there's stuff inside the secant. The derivative of secant x has a shortcut that's well known. The derivative of secant x is secant x tangent x. So the derivative of secant stuff is secant stuff tangent stuff. And by the chain rule, I multiply by the derivative of the stuff. All right. So lots to keep track of, lots to step-by-step figure out. All right, so that's that derivative. I have to differentiate negative x. The derivative of negative x is -1. So why don't I just change this to a minus instead of a plus, just to make it easier and not have to write so many steps to simplify. And then I have minus e sine 2 pi x, tangent 2 pi x. Don't do much, but I do need to differentiate at the end by 2 pi x. And the derivative of 2 pi x, the derivative of 7x is 7. The derivative of 2 pi x is 2 pi. 2 pi is a number, 6.28 something. So this is just 2 pi. So I'll put the 2 pi over here. I'll put maybe the pi over here and the 2 over here. So that's my 2 pi stuff from differentiating. Hopefully I'm not losing anyone by moving stuff around a little bit. But you can go back and see where I got the 2 pi from. And I'm just following tradition, putting the integer number in front and the other numbers, e and pi, those irrational numbers afterwards. So that's the e part and the derivative of 2 pi x, the 2 pi part. So then I need to line up the rest of the stuff, which is sine 2 pi x, secant, I differentiate secant. So I get secant 2 pi x and then tangent 2 pi x. And there's no more derivatives to do. So that is my answer for the first derivative, just like that. This problem does ask to find the first and second derivatives. So once I have the first derivative formula, I can differentiate again to find the second derivative formula. So that would be something like doing the derivative again on the left-hand side and doing the derivative as well on the right-hand side. So differentiate again will give me the second derivative. Okay, so d of dy is written as d squared y. A little bit strange why that's done, but that's the way they write it. I mean, there's a reason behind it. Math people have reasons for all their stuff. Dx becomes dx squared. So the notation we need to use for the second derivative looks a little bit unintuitive, with the top square being between the d and the y, and the bottom square being after the dx. As I said, there's reasons for this madness. That's just the way it looks. And people say, oh, I really just want to use y prime, double prime, because it's just so much easier. Yeah, I mean, it's equivalent. I'm just saying that as we do more complicated formulas, they don't work with y double prime. the formulas only work with the dx's and dy's and those kinds of things. So unfortunately, we're kind of stuck with this. That's called the Leibniz notation. This is the Newton notation. This is the Leibniz notation. So we're kind of stuck with the Leibniz notation because more sophisticated calculus doesn't work with the Newton notation. Okay, let's go ahead and do some derivatives. So the derivative of negative 3x to the negative 4, this one right here, it's a power rule with a constant in front. So I multiply these constants together. Negative 4 times negative 3 is positive 12. And I'll subtract 1 off the exponent again. Here we have the derivative of e to the negative x. Whoops. The derivative of e to the minus x is, again, a chain rule problem. So it's e to the minus x times the derivative of minus x, which we already know is minus 1. So I guess you didn't have to write this out. If you're very comfortable doing this, you could just say, oh, that's going to be a minus 1. So this turns into a plus. So underneath, we're going to get sort of a plus. Let me get a little mark. Plus e to the minus x after we simplify it. So, you don't have to show every single little step if you're comfortable, but don't try to rush things and make little mistakes. That will be sad if you do all this math stuff and make a little mistake because you just tried to skip a step. So know your limits, please. Okay, so we're going to subtract the derivative of all this stuff. 2 and e and pi are all constants, so they're being multiplied and do not affect any derivative. And what are they being multiplied onto? The derivative of this secant 2 by x tangent 2 by x, which is a multiplication of two functions and thus requires the use of the product rule. So I'm going to do the derivative of the first. The derivative of secant, remember, is secant tangent. So we get a secant tangent. Now, I intentionally said that kind of vague because that's what most people say, derivative of secant is secant tangent. But what they really mean is the derivative of secant x is secant x tangent x. This, my friends, is not x. It's 2 pi x. Anytime you replace x by anything else, you need to multiply by that derivative of the substitution thing, the new function that's inside. In this case, it's 2 pi x. So a sneaky little chain rule problem there. So make sure you don't lose that. So that's the derivative of the first thing. Derivative secant 2 pi x is secant 2 pi x tangent 2 pi x times the derivative of the inside function. And the product rule says you take the derivative of that first part and then you multiply it by the second part. And then you add to that the derivative of the second part multiplied by the first part. All right, so it looks like I need more space because this is a long problem. So the derivative of the tangent, that's the second function, second part of this function. The derivative of tangent is secant squared. So secant squared 2 pi x. You could also write the square on the outside if you wanted to. The square can be either place, but math people love to do their little abbreviations and put the square there. Again, if you hopefully you're not getting tricked anymore. If you got tricked before, since it's not just secant x, because it's not just tangent 2 by x, the answer is not secant squared 2 pi x. You have to multiply by the derivative of the inside function. And then we'll multiply by the first part of the function, which is secant 2 pi x, and that would be our product rule. Oh, oops. Yeah. So the derivative of the second times the first. Yes. I almost lost it there. Okay. So let me go back to this and try to clean it up a bit. I do have a few derivatives still to do, so let me do those. Let me see if I can shrink this a little bit. No. Okay. I thought I paused the recording. This is going to look really silly. I paused the video share because I was trying to figure out where the make smaller button is. This is going to be kind of silly. Well, it's me. I make lots of mistakes. I just try to go slowly enough that I can find them to fix them. My little like make things adjusting in size was hidden behind one of the um, formatting bars, so I couldn't find it. And I thought I paused the video so you could figure it out. And then, of course, you're staring at me doing nothing for a while. Okay, it is what it is. So I'm gonna try now to simplify this thing. Um, d squared y, or oops, d squared y, said it right, over dx squared equals, see now I'm a little rattled. I wrote it here on the left. Let me write here on the right. Let me use a different color so it's easier to see. I'll get this right. I apologize if this is like silly because it's not perfect polished. So this thing right here is still the same, 12x to the minus 5. We already simplified this part because the derivative of minus x is minus 1. This is just a constant. Inside, we have the secant tangent thing. We have a derivative of 2 pi x, which is just 2 pi. We have times, oops, we have times tangent 2 pi x. And then we have plus some more stuff. This is secant squared times another derivative. Derivative 2 pi x is just 2 pi. And then we have the secant 2 pi x. Parentheses over there. Okay, so that is the second derivative. There's no more derivatives for me to do. Let me see if I can shrink this and make it, yeah, so there's the whole visible thing. There's a couple of things I can move a 2 pi in front of things. There's not a lot of simplification to do. And I think I've already spent enough time on this problem not to rewrite it again with a bunch of small simplifications. So I'm going to leave it there for the second derivative. Mostly simplified, maybe technically not simplified all the way. Okay, I have a last couple of problems here for this video, and they are on the second of our two main learning objectives. So if you remember from the beginning, using derivative shortcut rules to find derivatives, I did 4 examples of that about how to find some derivatives using the shortcut rules. And now I'm going to do a couple of problems on determining increasing, decreasing, and critical points of a function. So that's this one right here. All right, so I have this function here, cube root of x minus x over 3, which if you remember your rules for converting radicals into fractional exponents, is the same as x to the 1/3 minus x over 3. So again, we don't really use calculus or a lot of math with radicals or roots. We convert them into fractional exponents. All right, so this problem asks us to find the critical points. Critical points sound important. They sound critical. So what is a critical point? Well, the function does interesting things at critical points. And a critical point can be found when the derivative is equal to 0 or the derivative is undefined. So we need to check 2 possibilities: when the derivative is undefined and then when the derivative is 0, and those are called our critical points. All right, so let's go ahead and find the derivative here. This one's pretty straightforward. X to the 1/3 has a derivative. 1/3 minus 1 is negative 2/3. You can check that if that's not immediately clear. So I subtract 1 off the exponent. This is a number times x. It's basically 1/3 times x, if you think of this as a number in front of x. So numbers being multiplied or divided to functions are not affected by the derivative. They don't go away, but they just kind of hang out there and stay multiplied. So this is still the 1/3, and the derivative of x is just 1. So that's my derivative formula. So I need to find out when this is equal to 0 and when it's undefined. All right, my handwriting is not the greatest with these pens, but I'll work on it. So we need this 1/3 x to the minus 2/3 minus 1/3 is undefined. So we have two problems now to solve. Let's do the one that's probably more easier for folks to remember how to do, which is the equal to 0 part. So having something equal to 0 just means we need to solve and need to get x's by itself. There's lots of ways of solving these things. I'm just going to add 1/3 to both sides. So let me get rid of this thing right here. And I'll do, oops, where's my pen? Boom. Add 1/3 to both sides. So I get 1/3 equals this stuff right here. And then I'll multiply by 3. And I get this. Again, lots of ways of solving this. I think I'll solve it in a way that helps people review a little bit. A negative exponent is the same thing as the fraction of the positive exponent. So I'm just going to simplify this as 1 over x to the 2/3. Right? Negative exponent can reciprocalize to be a positive exponent. And now I will multiply by x to the 2/3. Some people have been wondering, what the heck is he doing with all this over here? I'm demonstrating one way of showing work. It's important to show work, especially in a math class, especially in an online math class. There's lots of ways of showing work. You can show it directly, by saying like ×3 and ×3 and stuff like that. Some people like to do that way. But you can also just do it in lots of other ways, as long as it's clear what you're doing. So I just want to show you another way. For example, you could just write on the side what you're doing. Okay, so I am going to multiply by x to the 2/3. That means I get x to the 2/3 times 1 is equal to 1. Okay, so now what do? I have to get rid of this power, this 2/3. What I can do is I can do it in 2 steps. I recommend this. I can raise it to the 3rd power. That would be getting rid of the fraction or the fractional part of this exponent, the 2/3. So that'd be x squared is equal to 1 cubed. 1 cubed is the same thing as 1. So I'll just write that as 1. Oops, it's supposed to be in blue. Got a color coordinate here. And then I have to get rid of the square. To get rid of the square, I'm going to square root. And that would give me the square root of x squared is equal to the square root of 1. And it's important to know what's going on here, because the square root of x squared is not x. The square root of x squared is absolute value of x. People are going, what? Well, a lot of math people don't write this as absolute value of x. They write this as a plus or minus x, because absolute value is, in this linear sense, just a plus or minus. And in fact, a lot of people don't write the plus or minus on the side where it should be with the x. They write the plus or minus on the other side. So this may look more familiar to people. When you're square rooting both sides, you get a plus or minus. So you get 2 answers, x equals 1, x equals -1. These are critical points. So we have 2 critical points right there by solving this equation equal to 0. Built in a little algebra review for you in this problem too. All right, let's see. I think make this bigger. All right, so I ran out of space for my undefined part. So I'll just move this over here and solve for the undefined one over here on the right-hand side. All right, so what makes things undefined? first of all, let me write this using the reciprocal property like we talked about before, just to make things easier to solve. So how do we know when things are undefined? Well, undefined, another way of thinking about undefined is it's not possible to calculate. There's no number that you could write as the answer or no nothing. It's undefined as a possible answer. So we just can't calculate. We can't do anything with it. So what makes math expressions undefined? What makes things impossible to calculate? Well, we don't know how to calculate division by zero. 3 divided by zero, maybe some version of infinity, but certainly you can't calculate it. Square root of a negative number is imaginary or complex, and the calculus with complex numbers is very complicated. It's a fascinating course, but we're not doing that. We're just doing real numbers. So square roots of negative numbers, not really able to define it in a regular calculus course. There aren't many things that are undefined. Some other ones are like the tangent of pi over 2 is undefined. The log of 0 or the log of any negative number is undefined. So there are a few things which are undefined. In this problem, we have a division by x. We have a division by x to the 2/3 more specifically, but that means we could divide by 0. So we could divide by 0. We divide by 0 when this thing is equal to 0. And remember, dividing by 0 means we get undefined. And undefined is how we find critical points. Remember, critical points is when the derivative is 0 or the derivative is undefined. So when is this undefined? It's undefined when we have 1 over 0. So when that bottom part, 3x to 2/3 is equal to 0, then we get a critical point. So I'll just, again, solve this thing. I'll divide by 3. I get x to the 2/3 is equal to 0. I will cube, that's 2/3, by the way, 2/3. I will cube both sides to get rid of the fraction thing there. And that gives me x squared is equal to 0. And then I'm going to square both sides. And this time we just get 0 because plus or minus 0 is the same thing as 0. So we get plus 0 or minus 0, which of course is just 0. So we get another critical point. So in this problem, we have 3 critical points. We have x equals 1, x equals minus 1, and x equals 0. So we have three critical points. And if you want to be technical about the math vocabulary, these are called critical values because a point has to have an x and a y. I would find the y just by taking these values like x equals 0 and plugging it into the formula. 0 to the 1/3 is 0, minus 0 over 3 is 0. So the critical point would actually be 0, 0. If I plugged in 1, I get 1 minus 1/3, which is 2/3. So we get different critical points if you plug in the y. But most math people kind of do points and values kind of interchangeably unless you are being very specific about something. So anyway, those are the critical values or critical points. And the answer to this first question, part A, on determining decreasing, and critical points. All right, so I mentioned before critical points, very, very useful for finding things. So what do they help us find? Well, they help us find all kinds of things, including where the function's increasing and decreasing. So the derivative is just a rate. It measures how y changes. So if y is getting bigger, if it's adding, getting bigger, then the derivative must be positive, right? Because you have a plus to the y is going to be a plus derivative. So derivative is positive, means it's increasing. If it's getting smaller, if it's subtracting, that's a minus sign. So the derivative would be negative. So we know that increasing is derivative is positive, and decreasing is where the derivative is negative. So this is where dy dx is positive, and decreasing is where dy dx is negative. Well, how do we know when the derivative is increasing or decreasing? I mean, we have this derivative formula. It's right here. How do we know when all that messy stuff is greater than zero and when all that stuff is less than zero? Well, it's going to be easy to find once we know our critical points, because this is a continuous function. And anytime you change from positive to negative, it has to go through zero, right? Positive, 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 negative, negative, negative. How did it get from positive to negative? It went through zero. The other possibility is it went through an undefined point. So it could just jump from positive to negative, which is why we need the undefined critical point as well. So going from positive to negative or negative to positive, it will have to go through zero or have to jump somehow through an undefined point. So we know all three of those places where it can possibly switch. So possible switching points. And this would be from increasing, decreasing. That would be x equals 1, x equals 0, x equals -1. I guess maybe whatever. I'll do a number line so you guys can visualize what's going on here. So at x equals 0, it could possibly switch. At x equals 1, it could possibly switch. At x equals -1, it could possibly switch. So those are the possible switching places. So what I'm saying is, if it was increasing here before -1, then it has to be increasing all the way up to -1, because -1 is one of the only three places it can possibly switch. Well, let's find out if it was increasing or decreasing at a number to the left of -1. Let's choose something nice to compute. Remember, our function right here is 1/3, or I guess we can write it over here too, right, with the non-fraction. Anyway, it's 1/3 x to the -2/3 minus 1. And we need to choose a number that's somehow, to the left of -1. Now you could choose like -1.1 and see whether it's increasing or decreasing. Maybe you don't like decimals. Maybe you can choose something like -2, because it's easier to do decimals. If you're using a calculator, I would choose something like -2. But if you're doing it by hand, you might want to do something that to cube roots really easily. You can choose any number you want in there. So you're going to use a number. For example, I'm going to use -8. And why do I use -8? As you will see in a moment, it's easy to compute. So I'm going to take my derivative formula and I'm going to plug in -8. And my derivative formula is right over here. So let me jump over to Desmos. And I have y equals 1/3 x to the exponent of -2/3, and then minus 1/3. Let me just double check that that is correct. 1/3 x to the -2/3 minus 1/3. Desmos. Yeah, so that's the graph of the derivative function. And you might be able to see that here, the derivative is equal. This is not the y-axis. I'm measuring the derivative here, right? So the derivative is equal to 0 when x is -1, when x is +1, and you can see it jumping out of control around 0. So those are the three critical points. I'm going to take this thing and plug in some values. So I'll convert it to a table. It's giving me some numbers here. You can see at -1 and at 1, it's both 0, and at 0, it's undefined. I'm going to get rid of some of these numbers. I can plug in like -1.1 if you want, or you can plug in -2, or you can plug in -8. It doesn't really matter. You'll notice that every one of these is negative. The derivative is negative to the left of -1. So over here, we know that it's decreasing. So it has to decrease all the way up to -1. And -1, derivative could be 0 or undefined. In fact, we know the derivative is 0 at -1. So what about between -1 and 0? It could switch to increasing. It doesn't have to, but it could definitely switch to increasing at this point. Let's see if it's still decreasing or if it really did switch. So now I need a number between -1 and 0. So I need to test something in this range between -1 and 0. So I'll use some negative number. Maybe I'll use a -0.5. And I do get a positive derivative, which means that here between 0 and 1, it's increasing. So it did indeed switch. It doesn't have to. It just did at that point. What about at 0? So I need to try a number between 0 and 1. And I'll need to try a number that's bigger than 1. So I'll try those both. So here's a number which is bigger than 1, bigger than 0, but not as big as 1. And here's a number that's bigger than 1. So you notice that when x is 0.5, the derivative is positive, and when x is 2, the derivative is negative. So this is going to be positive or increasing, and this is decreasing. So now we know where the graph is increasing, decreasing, and I can write my intervals. So for decreasing, I'm going to go from -infinity all the way up to, let me make that look better, all the way up to -1. And also I go from 1 to infinity. So those are all my decreasing intervals. And for increasing, it's these two parts in here. I mean, essentially I have to get rid of 0 because 0 is an undefined point. So I'll go from -1 to 0, as well as from 0 to +1. So those are my intervals of increasing and decreasing. And that answers this question B, which is, oops, there it is, find the intervals where the function's increasing and where it's decreasing. All right, well, that's the last problem I have prepared for these lectures, for the lecture on differentiation review. Hopefully you now have a better idea how to find, how to use the derivative shortcut formulas to find derivatives and how to determine increasing, decreasing, and critical points. Please reach out if you have any questions or have any what-if scenarios, want to try some additional problems, or of course, if you have questions on anything else. All right, well, hopefully you have an enjoyable day, and hopefully I will see you again very soon.